because of some problem of the Zoom link, we are starting about 5 minutes after the scheduled time. And it is our great pleasure to have our speaker today. And his name is Professor Kazunari Domen, one of the top scientists in the world. And he is at the University of Tokyo as well as Shinshu University as a university professor and special contract professor respectively. And the title of his talk is Photocatalytic Water Splitting to Produce Solar Hydrogen on a Large Scale. So as title indicates, it's a very, very timely topic for all scientists in the world. And let me briefly go into his career. And he educated from Tokyo University, a PS from 1976, master's degree, same department, same university in 1979, then PhD from same institute in 1982. Then immediately after his PhD, he got associate researcher. Associate researcher is sort of assistant professorship in Korea. And in Japan, they call it, I think, Joshu. Is that right? and he got at Tokyo Institute of Technology in Chemical Resources Laboratory. Then he spent a year during this period as a visiting scientist in IBM Almaden Research Center in the United States. Then he promoted to associate professor in 1990 at Tokyo Institute of Technology, then finally to professor in 1996 until he was recruited to University of Tokyo as a professor in Department of Chemical Systems and Systems Engineering, School of Engineering. Then 2017, from 2017, he was a special contract professor, Center for Energy Environmental Science in Shinshu University. Then 2019, as a special contract professor of Research Initiative for Supramaterials in Shinshu University, and same as a university professor at the University of Tokyo. And he received many awards, and I listed only several. In the first one in 2007, Encouragement Award from Catalysis Society of Japan Award. Then 2011 Chemical Society of Japan Award, and 2018 the Japan Petroleum Institute Award, and 2019 Li Shun Lecture Award, and Advance of Catalysis Award of APACS. And then 2020 Honorary Fellow of Chinese Chemical Society. And he has published almost 800 research papers and in many patents. And his research interests are development of photocatalysts for water splitting under visible light irradiation, then development of novel catalyst, then surface reaction dynamics. So we are very honored to have you today, Kazunari, and I will close the screen sharing now so that you can proceed for yourself.
Okay, now let me share my slides.
Yes.
Can you see this one?
Yes.
Okay. Okay.
Oh,
So
digist. A,
this
B,
is
C, D, A, B, C, D, dog.
Oh, so very sorry, very sorry.
Okay.
I'm very sorry.
My pronunciation was not correct. Sorry.
I'm very sorry. And yes, thank you very much, Professor Kim, for very kind introduction. And that now let me start my lecture. The title of my talk today is Photocatalytic Water Splitting for Solar Hydrogen Production on a Large Scale. Here I show the outline of my talk. After a brief introduction about solar energy and water splitting reaction, at first I'd like to discuss about a particulate photocatalyst for water splitting reaction using these three examples. Then I move to the photocatalyst sheet and water splitting panel. I use these two examples. Then I'd like to introduce our recent attempt for the construction of a prototype solar hydrogen production system. After that, I will summarize my talk. At first, introduction. Okay, at first, let me discuss about the amount of the solar energy. Actually, we are receiving the solar energy on the surface of the Earth every year with the amount of about 3.0 times 10 to the 24th joules per year. And at present, we are now consuming the energy of amount of 5.5 times 10 to the 20th. So comparing these two numbers, that the solar energy is now more than 5,000 times larger. And on the other hand, that actually on the Earth, the natural photosynthetic reaction is the biggest reaction to fix the solar energy into chemical energy. That amount is 3.0 times 10 to the 24th joules per year. So comparing these two numbers, about 0.1% of solar energy is actually converted into chemical energy by natural photosynthetic reaction. So comparing these numbers, if we will be able to fix about 0.02% of solar energy, it will be possible to support our modern life. However, the problem is that how wide area we need to use to collect the solar energy. So if solar energy will be one of the major energy resources in future, we need to develop the technology which is available for several 10 to the 5th square kilometers. To imagine this area, let's assume this kind of things. Assuming to provide 1/3 of the total energy, which is expected to be consumed in 2050, and then we use a 10% solar energy conversion efficiency system, and with a scale of 25 square kilometers. At present, the world's largest gigasolar PV system is existing at UAE, and the area is about 7.8 square kilometer. So this 25 square kilometer is more than 3 times larger than the present world largest system. But even using this kind of system, we need to construct about 10,000 plants to satisfy this amount of the solar energy. So probably the most important point to realize the solar energy is the scalability. And we need to develop the technology which is has a scalability to extend to this area. And another point, important point is that if we will be convert the solar energy only into electrical energy, it will cause some problem. So we have to mainly convert the solar energy into the storable and transportable energy. And in that case, at present, chemical energy is one of the most promising candidates. And especially, people believe that these kind of small molecules, such as hydrogen, methanol, methane, or ammonia, are the good candidates. And especially among these chemicals, hydrogen has a special position. This hydrogen should be produced from water by water splitting reaction without accompanied by the evolution of carbon dioxide. If we have this kind of hydrogen, it is not so difficult to produce a methanol or methane in combining with carbon dioxide and or ammonia in combining with the gaseous nitrogen in air using the thermal catalysts, which are they are more or less almost the practical levels. So the main problem is that how to split pure water using solar energy into hydrogen and oxygen. And then you consider that it is probably that the most realistic way is using the solar cell or photovoltaics, or maybe including the wind power, electricity, and then electrolyzed water. Of course, this is the at present the most realistic way, and this technology are already commercialized. However, the problem is that even now that the hydrogen produced by this process is still much more expensive than that's produced by the from the fossil resources by using so-called reforming reaction. And at present, that there are several ways to split water using solar hydrogen is being studied. And one of that one is photoelectrochemical water splitting reaction. And another one is so-called artificial photosynthetic reaction or photocatalytic water splitting reaction. In this case, there are many people are actually working and using many different materials. And today, my talk will be focused on this inorganic solid state materials. I mean that semi-conducting photocatalyst, because my major is solid state heterogeneous catalyst. So that's our target reaction is very simple. We like to split pure water into hydrogen and oxygen using solar energy on heterogeneous photocatalyst. Of course, the motivation is as follows. If hydrogen is produced from solar energy and pure water, it can be clean and sustainable energy carrier as well as chemical resource. However, from the viewpoint of technology, the situation seems to be more serious because we need to produce solar fuels on a large scale at a low cost in the near future. Actually, in our project, we are developing various kinds of semiconducting materials to split water into hydrogen and oxygen. And we are applying those materials into two different ways. The first one is photocatalytic water splitting reaction. In this case, we use this kind of particulate photocatalyst. And another one is a photoelectrochemical water splitting reaction. And in this case, we construct this kind of photoelectrodes. And frankly speaking, if we like to get a higher efficiency of solar to hydrogen energy conversion efficiency, this type of photoelectrochemical system is easier at a laboratory scale. However, if we like to extend this kind of system to a wide area, we have to face some serious problem. And consider that if we have to extend this kind of system to so large area, then the scale up is some problem. However, on the other hand, that in the case of a photocatalytic water splitting reaction, the extension to the wider area is not so difficult, but the problem is how to enhance the efficiency of these photocatalysts. So today, I would like to focus our attention on photocatalytic water splitting reaction, then photocatalyst sheet and water splitting panel. At first, let me discuss on this type of one-step overall water splitting reaction. In this case, both hydrogen and oxygen are evolving on the same photocatalyst. So this is probably the simplest way to split water into hydrogen and oxygen, but probably the most difficult way to split water. Here, let me just introduce the basic principles of one-step overall water splitting reaction very briefly. And this is a normal hydrogen electrode. That means the pH equals to 0. So that the proton hydrogen redox potential located at 0 volt and oxygen water redox potential located at plus 1.23 volt. This is a band gap position of a particulate photocatalyst referring to this axis. Under photoirradiation, electrons in the valence band are excited in the conduction band. Then conduction band minimum locate more negative than this hydrogen evolution potential. These photoexcited electrons have the thermodynamically possible to split to produce hydrogen. However, as I showed here, in almost all cases, as far as we use N-type semiconducting photocatalyst, we need to introduce so-called co-catalyst for hydrogen evolution to facilitate electrons transfer to protons and to generate hydrogen molecules. On the other hand, if the valence band maximum locate more positive than this O2 evolution photocatalyst, then again that these photoexcited holes are thermodynamically possible to oxidize water molecules into O2 molecules. But in many cases, especially in oxide type semiconducting photocatalysts, the surface of the photocatalyst itself works as O2 evolution site. So here I don't show any co-catalyst for O2 evolution. However, if we like to go get a higher efficiency of water splitting, it is many times better to introduce co-catalysts for O2 evolution. Today I'll discuss on both cases, so please keep it in mind. Okay, now let me move to the next part, particulate photocatalysts for water splitting reaction. At first, the metal doped strontium titanate. Probably, as you know, that the strontium titanate is a white colored powder, so this material's absorption edge is located at about 380 nanometers, so that these materials can absorb only UV light, and then these materials can use only a small portion of sunlight. However, the band gap position of these materials is suitable to split water into hydrogen and oxygen. So these materials have the potential to be a UV light responsive water splitting photocatalyst. And the structure of this material is a very well-known perovskite type structure, and the A site cation is strontium 2+, and B site cation is titanium 4+. But these A and B site cations are very easily replaced by various kinds of different cations. Here I show that our experimental result, and this is the X-ray pattern of the several doped strontium titanate prepared by solid state reaction. I mean that the calcination in air. This is undoped strontium titanate, and this is gallium 5%, lanthanum 5%, and gallium and lanthanum 5% doped samples. However, as you see here, as far as we see that these X-ray patterns, we observe only single phase of perovskite type structure, and there seems to be also no difference. Even after observing that SEM images, this is undoped sample. This is gallium 5%, lanthanum 5%, gallium and lanthanum 5%. We are not able to distinguish to each other. However, if we measure the activity of water splitting reaction by modifying only using rhodium and chromium mixed oxides, this material works very good hydrogen evolution co-catalyst. Then in this case, we don't use any co-catalyst for O2 evolution. We observe very significant difference of the activity. When we use a stoichiometric strontium titanate, actually that this is hydrogen, this is oxygen evolution, so that it evolves both hydrogen and oxygen in 2:1 ratio. So this is a standard activity. Then when we replace the titanium 4+ cations by lower valent gallium 3+ cations, as you see, that the water splitting activity was enhanced like this one. On the other hand, when we replace the A site strontium 2+ cation by higher valent lanthanum 3+ cation, activity was almost lost. And a similar tendency was observed using different combinations. In this case, we used the sodium 1+ cations to replace A site cation and tantalum 5+ cations to replace B site cations. And this is again that's the reference activity. Then if we replace the strontium 2+ A site cation to the sodium 1+, we can get better activity. However, if we replace the B site titanium 4+ cations by tantalum 5+, the activity decreases like this one. This kind of tendency can be generalized like this one. The doping of a lower valent cation For example, A side strontium 2 plus by sodium 1 plus, B side titanium 4 plus by gallium 3 plus, we can get higher activity for overall water splitting reaction. On the other hand, doping of a higher valent cation, for example, A side strontium 2 plus by lanthanum 3 plus, B side Ti 4 plus by tantalum 5 plus, the activity of water splitting reaction becomes slower. So in the case of the doping of lower valent cations, it is tends to increase the oxygen vacancy or decrease the titanium 3 plus cations if they exist in our strontium titanate. But discussion about this origin of this type of activity change is a little complicated. So today let me just say that although this kind of lower valent cation doping is a so-called P-type doping, but our material still shows N-type character. Okay, so let me now move to the more concrete example, aluminum doped strontium titanate. This aluminum 3 plus cation replaces this titanium 4 plus cation. So this is the lower valent cation doping. So we can expect that the activity will be enhanced. In addition to that, here I would like to show that so-called flux method preparation procedure. Here I show that the preparation procedure of our materials. At first, we purchase stoichiometric strontium titanate and then add a large amount of strontium chloride as a flux. Then we mix these two materials in an aluminum crucible, then calcine in air at 1423 Kelvin for 10 hours. By this method, at first we didn't realize, but some amount of aluminum in this aluminum crucible is dissolved into strontium titanate. So we call this materials as aluminum doped strontium titanate prepared by flux method. Here I compare the activity of the overall water splitting reaction. Again, in this case, we modify only by hydrogen evolution co-catalyst. And the light source is a xenon lamp longer than 300 nanometers. That includes the UV light. Here I show that the activities, and when we use a stoichiometric strontium titanate, in this axis, millimole per hour, the activity seems to be almost negligible. But as I showed previously, we can get hydrogen and oxygen evolution in 2-to-1 ratio. But after aluminum doping by solid state reaction, obviously the activity is enhanced like this one. However, when we use the flux method, as I showed in the previous slide, obviously that activity enhancement is much better. And at this stage, that apparent quantum yield at 365 nanometer was 30%. This is already considerably good quantum efficiency, quantum yield at 365 nanometer, which is included in sunlight. But of course, we further try to modify this method. Of course, we intentionally introduce alumina into these flux materials. But I should say that this added alumina seems not to be worked as a dopant, but it seems to be worked as a shape controlling reagent. Let me show the evidence for that. Okay, on the left-hand side SEM image, I show that the sample prepared by only using the strontium chloride as a flux. And this is a 5 micrometer scale bar, so that the particle size is considerably large and not really homogeneous. And in this case, the amount of doped alumina was about 0.3 atomic percent. However, if we add 1% alumina against this strontium chloride, then that, as you see here, the particle size becomes much smaller and almost homogeneous. And the amount of doped alumina was about 0.1%. So that this is the reason that I said that this alumina seems to be worked as a shape controlling reagent. Then we use this small size of aluminum doped strontium titanate. Then we can get, in this case, that already that the apparent quantum yield is exceeded 50%. So this is a very good quantum efficiency for overall water splitting reaction at this wavelength region. But so far, what we did is that that improved the property of the strontium titanate itself, so that we have just focused our effort for the improvement of the photocatalyst itself. Then we modify our co-catalyst. I mean that we will add the oxygen evolution co-catalyst. At first, we have found that when we added the molybdenum oxide as an oxygen evolution co-catalyst. The loading amount was only 0.1 weight%, very small amount. But as you see here, the apparent quantum yield was very close, almost 70%. And this is a very good quantum yield for overall water splitting reaction. However, more recently, we realized that when we switch this molybdenum oxide to cobalt oxide, more precisely cobalt oxyhydroxide, and all the metallic components of the co-catalyst, I mean the cobalt and rhodium and chromium, were photodeposited. Apparent quantum yield exceeded 90%. This is extremely high quantum efficiency for overall water splitting reaction. So now let me discuss a little more in detail about this photocatalyst. Okay, this is the wavelength dependence of the apparent quantum yield. And this is the data that I showed in the previous slide at 365 nanometer, 91% of AQY. We also measured at different wavelengths as shown here. And now apparent quantum yield was evaluated based on the total photon number which was introduced into our reactor. That means that some portion of the introduced photons are scattered out without being absorbed by our photocatalyst. So if we evaluate the quantum efficiency based on the total photon number, which was really absorbed by our photocatalyst, and we say that it's internal quantum efficiency, at least in this region, we believe that internal quantum yield is about almost 100%. So I would like to say that it is now possible to split pure water into hydrogen and oxygen with a quantum efficiency of almost unity using a particulate photocatalyst. Now let me explain a little bit in detail how to prepare this type of photocatalyst. As I said, that all the metallic components of the co-catalyst are photodeposited in an aqueous solution. At first, we construct the hydrogen evolution co-catalyst. That is a rhodium chromium coaxial structure. In this case, at first we deposit the metallic rhodium nanoparticles by using a photoexcited electrons to reduce rhodium 3+ into rhodium 0, rhodium metal. But if this rhodium metal nanoparticle is exposed to the surface, then that's a reverse reaction. I mean that the hydrogen and oxygen to form water molecules proceed. So to prevent the reverse reaction, we coat this metallic rhodium nanoparticles by chromium oxide hydroxide. That is a chromium 3+ containing materials. In this case, again, we use photoexcited electrons to reduce chromium 6+ into chromium 3+. By these two reactions, we can construct a coaxial structure for hydrogen evolution. But in any case, these two reactions using photoexcited electrons. So these two reactions are so-called photo reduction reaction. After that, we construct the auto-evolution co-catalyst. That is a cobalt oxide, cobalt oxyhydroxide. In this case, we use a photoexcited holes to oxidize cobalt 2+ into cobalt 3+. So this reaction is actually photo-oxidation reaction. So through this construction of the co-catalyst, here I show that the change of the feature of our photocatalyst. This is a SEM image of unloaded aluminum doped strontium titanate. As you see here, this is a very well crystallized particle, but there exists many different facets on this surface. Then, after metallic rhodium nanoparticle deposition by photoreduction method, you see only some limited facet, these small particles does exist. Then, even after we coated this metallic rhodium by chromium oxide, again, a photoreduction reaction, we still observe that this kind of particles on some limited facet. However, when we introduce a cobalt oxide for auto-evolution by photo-oxidation reaction, almost all facets contains some particles. That means that this cobalt oxide is actually deposited on the different facet from that rhodium and chromium coaxial structure. To understand this situation in more detail, we carried out a high-resolution STEM measurement. This is one particles of our photocatalyst, and from this area, we took electron diffraction pattern, as shown here. And from this electron diffraction pattern, we can identify that this flat facet and these flat facets 100 facet and their family. And I hope that you can see that some small particles does exist on these surfaces. And these particles are actually only hydrogen evolution co-catalyst, rhodium and chromium co-catalyst. And there exists some other somewhat curved facet as shown here. And on these facets, this is a little bit difficult to identify, but here let me say that this is 110 facet for simplicity. And on this 110 facet, we observed only cobalt oxide, O2 evolution co-catalyst. That means that the photoexcited electrons and holes are transported to different facets with almost 100% efficiency. So the question is that what is the driving force? We consider that there should exist some internal electric field inside of this particle, but this particle size is about a few hundred nanometers. So it is almost impossible to measure, experimentally measure that internal field. So we decided to carry out a simplified two-dimensional simulation of such a kind of internal excited internal electric field. This is our model structure. The particle size is 500 nanometer. Here we have 100 facet, and this is 110 facet. This is X prime axis. This is Y prime axis. And then we assume that the work function difference, this 100 and 110 facet, is 0.2 eV. And that seems to be reasonable from the literature values. Then we carried out the simulation. And as you see here, along with X prime axis, the internal electric field is downward like this one. This kind of internal electric field accumulates photoexcited electrons on the surface. On the other hand, along with Y prime axis, the internal electric field is actually upward. In this case, the photoexcited electrons are likely accumulates the photoexcited holes on the surface. So but this is actually two-dimensional system. So the actual situation is like this one. And then we also evaluated the ratio of the photoexcited electron holes accumulation. I don't get into the detail of these numbers, but from these numbers, we are sure that actually photoexcited electron holes are separated with almost 100% efficiency. So that's the origin of the almost 100% internal quantum yield of water splitting reaction is this type of internal electric field. Now let me move to some different photocatalytic materials. Tantalum 3 N5 prepared on potassium tantalate. Actually, so far I have discussed just this type of strontium titanate photocatalyst. On the other hand, tantalum N5 is red colored materials, and it is absorption edge located at about 600 nanometer. And then the band gas crystal structure of this material is like this one, so-called anisotropy structure. And band gap energy was about 2.06 eV. And we had been working on this type of materials for more than 15 years, but we had never succeeded in splitting water into hydrogen and oxygen. And at first, let me introduce our conventional preparation procedure of TS-N5. In this case, we use starting materials as tantalum 205 materials, then nitride by atmospheric pressure of ammonia at 850 to 900 degrees C. In this case, at first, tantalum ON, TaON is formed, and then tantalum N5 is formed. And to see this change in detail by UV diffuse reflection spectra, I show that change of the diffuse reflection spectra of these materials. And in this case, we intentionally slowed down the nitrization rate to see the change clearly. Okay, this is a starting material, tantalum pentoxide, a white colored powder. Then after starting the nitrization, that new peak appears here. Then after about 15 hours, the absorption edge locates at about 500 nanometer. Then we obtain this kind of yellow colored powder. This is actually tantalum oxynitride. Then after that, a new band appears here. Then after 100 hours nitrization, the absorption edge shifted to about 600 nanometer. Then we get this kind of red colored powder. This is TS-N5, which is confirmed by XRD pattern. And we also examined the band gap position of these materials by electrochemical method as well as UPS. In this case, only UPS was available. Then if we compare the conduction band minimum, even we carry out the nitridation, the conduction band minimum was almost unchanged. On the other hand, the valence band maximum shifting up with increasing the nitridation. However, that even in the case of the tantalum 3N5, these materials still have a suitable band gap position to split water into hydrogen and oxygen. Here I show that the high resolution TEM images of these three materials. This is tantalum pentoxide, and from this area, if we take electron diffraction pattern, we can get this kind of sharp spot. That means that this part is actually a single crystalline part. And when we move to the tantalum oxynitride, the tantalum to anion ratio is in this case 2.5, but in this case it becomes 2.0. Then that's the these materials, tantalum oxynitrides, becomes porous materials like this one. However, when we took the electron diffraction pattern from these porous particles, we still observe a sharp spot like this one. So this particle is actually porous single crystalline particles. And even in the case of tantalum 3N5, from this particle, we obtained that again that this kind of sharp spot. So we consider that we are preparing a considerably good quality particles. That's why that we had been working on this type of materials for more than 15 years. However, as I said, we have never succeeded on overall water splitting reaction. However, very recently, we have realized that when we change the starting materials from tantalum pentoxide to potassium tantalate, then that the nitridation again at 850 degrees C, but very small period, 0.5 hour to 4 hours, we realize that we can prepare the tantalum N5 on top of potassium tantalate. Now let me see such a kind of materials. Okay, this is the starting materials of potassium tantalate. After 0.25 hour nitridation, I mean that 15 minutes nitridation, you see that there exists some nanorod is starting to grow. And after 1 hour, we can observe that clearly that this kind of nanorods are existing. And if we take UV spectra again, okay, this is a potassium tantalate. Then when we started the nitridation, you see from the very beginning stage, the absorption edge is already extended to 600 nanometer. This seems to be indicating that we are directly preparing tantalum 3N5. To get more clear evidence, we carried out STEM measurement. And okay, this is a potassium tantalate. This is a nanorod, which was prepared by the nitridation method. And this is, you see, this is a nanorod structure, and this is completely single crystalline particle. And if we look at this figure, that until the uppermost layer, this materials is very, very crystallized. And more importantly, from the lattice constant of these materials, this is exactly tantalum 3N5. So we decided that to use this tantalum 3N5 particle prepared on the potassium tantalate to prepare our photocatalyst for water splitting reaction. Then in this case, again, we deposit metallic rhodium nanoparticles at first. But in this case, we use a only visible light to excite only this tantalum 3N5. So to deposit the metallic rhodium nanoparticles only onto the tantalum 3N5 nanorod. Here I show that the SEM image after metallic rhodium nanoparticle deposition. I hope that you can see that these small particles, this is 2 nanometer scale bar, so there are 2 to 3 nanometers particle. And this is a more wide space, and then this part is potassium tantalate, but only these small particles are located only on this nanorod. That means that this structure is that what we expected that for this at this stage. Then to cover this surface area, we also used the chromium oxide layer, not core shell structure again. And in this case, we didn't use any co-catalyst for O2 evolution. And Here I show that the time course of water splitting reaction. We use only distilled water and irradiated by only visible light. As you see here, both hydrogen and oxygen evolution takes place exactly in 2:1 ratio. This is the first example which has succeeded in overall water splitting reaction based on tantalum 3N5 nitride materials. However, there remains a problem. The problem is that this one, at 420 nanometer invisible light region photon, the quantum yield is still 0.25%. So we still have a lot of room to improve the quantum yield. And now let me move a little bit different materials, yttrium titanium oxysulfide. This material has a so-called layered perovskite type structure. This yellow ball is actually sulfide anion. And this is a photograph of this powder materials. This is a little dark brown colored powder materials. And the absorption edge is extended to about 640 nanometers. And we prepare these materials at 800 degrees C in a vacuum sealed coarse tube for almost one week, so that the particle size becomes considerably large. This is 20 micrometer scale bar. So that's the particle size is about 5 to 10 micrometer. This is not really suitable to use as a photocatalyst. However, when we took the electron diffraction pattern from different position of one particle, like this one, then it shows almost the same diffraction pattern. So these particles seems to be almost single crystal particles. However, when we examine in more detail these materials, we realize that this material's property is not so good. This is actually a STEM image using a cross section. And inside of this particle, as you see here, this kind of holes exist. This is not very special particle, but we very often observe this kind of holes. And this white colored part is actually a dislocation part. So that means that our oxysulfide material property is still very poor. But however, when we modify our photocatalyst, again by rhodium and chromium mixed oxide core shell structure, and in this particular case, we used iridium oxide nanoparticles as an oxygen evolution core catalyst, which was adsorbed from the iridium oxide nanocolloid solution. Then when we irradiated by visible light, you see that both hydrogen and oxygen evolution takes place in 2:1 ratio. This is the first example of the overall water splitting reaction based on oxysulfide materials. However, as you see here, when we continue the reaction for 20 hours, the activity was decreased to about 80%. And but this degradation is not really due to the degradation of these oxysulfide materials, but our iridium oxide oxygen evolution co-catalyst seems to be degraded because, as I said, just we adsorbed this iridium oxide nanocolloid onto this surface. So we probably need to improve our preparation procedure of co-catalyst. And another problem is that this one, again, that at 420 nanometer, apparent quantum is still there remains at about 0.36%. So we have still, again, a lot of room to improve the activity. But okay, so far I have discussed 3 different types of photocatalyst particulate system, but our purpose is to apply this particulate photocatalyst into a large area like this one. To extend to such a large area, there seems to be several different ways. But probably one of the simplest way to consider, we can consider is this kind of water splitting panel. That is more similar to the photovoltaics panel. But to construct this kind of water splitting panel, we need to fix this two-dimensional, these particles, photocatalyst in two-dimensional. We call such a kind of system as a photocatalyst sheet. Now let me move to the next part, photocatalyst sheet and water splitting panel. At first, I like to introduce a little bit different types of water splitting reaction. In this case, we use 2 different types of photocatalysts. I mean that we use this 2-step or so-called Z-scheme water splitting reaction. And here, that system that I introduced is not really our original system, but this system was originally reported by Professor Kudo's group at Tokyo University of Science. And they used bismuth vanillate for O2 evolution photocatalyst, and rhodium doped strontium titanate modified by ruthenium for hydrogen evolution photocatalyst. And these two photocatalysts are actually connected by iron 2+, 3+, so-called redox shuttle. And they put all these three components into the suspension system like this one, and pH equals low, I mean acidic solution to maintain this iron 2+, 3+, without the precipitation. Then after optimizing the reaction condition, they carried out a water splitting reaction using solar simulator. And in this case, for about 150 hours, both hydrogen and oxygen evolution takes place exactly in 2:1 ratio and almost a stable activity. Then in the beginning of this reaction, the quantum yield at 420 nanometers, about 4.2%. And this is a typical quantum efficiency in a suspended system, I mean the aqueous solution, for using the two-step overall water splitting reaction. Then we decided to utilize this kind of system to construct our photocatalyst sheet. In this case, we a little bit more modified our photocatalyst. We co-doped lanthanum and rhodium into strontium titanate to make a hydrogen evolution photocatalyst. And in the case of oxygen evolution photocatalyst, we use the molybdenum doped bismuth vanillate. Although the color is somewhat different, but if we measure by UV spectroscopy, the absorption edge in both cases locates at about 520 nanometers. Then here I show that the preparation procedure of our photocatalyst sheet. We mix these two particulate photocatalysts in an isopropanol solution, then just drop cast on a glass plate and then drying. Then that we can get this kind of mixed powder layers. The thickness is about at most 10 micrometer. After that, we deposit it conducting layer by sputtering or the evaporation. In this case, a gold or carbon, like this one. Then after annealing at some temperature to stick is better with these photocatalysts, we put another glass plate. In this case, this glass plate has a double-sided carbon scotch tape. So push, then peel off, then we can get this kind of structure. And after removing some remaining physisopt particles by ultrasonication, we can get this kind of photocatalyst sheet prepared on a glass plate. In this case, the particles size was about 3 centimeter times 3 centimeter. Then this is a SEM image. This is a top view. As you see here, that the structure is not really so well organized. This red dot indicates the molybdenum doped bismuth vanillate for O2 evolution photocatalyst. And this green dot indicates the lanthanum rhodium co-doped strontium titanate for hydrogen evolution. And in this particular case, we use gold as a contact layer. So this is a whole structure of our photocatalyst sheet. But when we put this photocatalyst sheet in an aqueous solution, just a distilled water without any electrolyte and irradiate by solar simulator AMS 1.5G, you see that both hydrogen and oxygen evolution takes place exactly in 2:1 ratio, and in this case for 10 hours. And another interesting point that when we change reaction temperature, the activity changes very much. So we measure the activity, temperature dependence of the activity. And as you see here, when we increase the reaction temperature, both hydrogen and oxygen evolution rate was increased as shown here. And this is the Arrhenius plot of this data. Then from this Arrhenius plot, we can get the activation energy of this water splitting reaction is 18 kilojoules per mole. Then at highest temperature, we could get the apparent quantum yield was about 33% at about 420 nanometers. This is much better activity than the system, or than the suspended system. And in this case, solar to hydrogen energy conversion efficiency was about 1.2%. This is still much lower comparing to the photovoltaics, but I will be back this number later. And this is one of the typical experiments using this kind of photocatalyst sheet. In this case, we use a carbon as a contact layer, and this is the evolving hydrogen and oxygen exactly in 2:1 ratio in just a distilled water, as shown here. Okay, now let me move to the another example of the photocatalyst sheet. In this case, we use aluminum doped strontium titanate. This aluminum doped strontium titanate is exactly the same with this aluminum doped strontium titanate. However, in this case, we needed to prepare a kilograms order of aluminum doped strontium titanate photocatalyst. So we, in this case, we deposited our co-catalyst by the so-called co-impregnation method. So it is not so sophisticated as I explained previously. Then that's the apparent quantum yield of water splitting reaction in this case was about 50 to 60%. But anyway, we use this co-catalyst loaded strontium titanate and nanosilica particles mixed in aqueous solution and then spray coated on a frosted glass surface, then dried and at 90 degrees C in air. That's all. Okay, it's a very simple preparation procedure. This is a 500 milliliter beaker just filled with distilled water. And then, if we put this beaker under sunlight or irradiate just solar simulator, we can get this kind of bubbles coming out. This is the hydrogen and oxygen, which is evolving due to the using the UV light included in sunlight, as like this one. So here I show that this photocatalyst sheet cross-sectional view. As I said that, sorry. We use, in this case, frosted glass. So this the surface is curved like this one. Then these white particles are photocatalyst, and then this dark gray part is nano-sized silica particles. Then this is more magnified STEM images. This is 10 nanometer scale. And this black part are the aluminum doped strontium titanate photocatalyst. And these are the nano-sized silica. As you see here, the particle size is about 20 nanometers. But there exists these kind of buoys. And these kind of buoys are actually filled with distilled water. And in addition to that, evolved hydrogen and oxygen molecules are actually dissolving in this distilled water, but that is actually supersaturated conditions. The reason that this hydrogen and oxygen does not form the bubbles is that this void is too small to make a seed of the bubbles. So that these supersaturated molecules actually goes outside upper layer like this one, so that this close to the surface layer is a supersaturated layer. Then that the bubble is actually formed on the surface of this our photocatalyst sheet. Here I show that just optical microscopy images, and this is 1 millimeter size. So you see that we have a very small number of bubble formation sites, about 4 sites per 1 square millimeter, like this one. Okay, this is a real situation to form the bubbles of hydrogen and oxygen. And based on this kind of photocatalyst sheet, we constructed the water splitting panel. This is a smallest water splitting panel. The size is about 5 centimeter times 5 centimeter. But in this case, we can control the thickness of the water layer from 5 millimeter to 1 millimeter. Now let me just show you only one example. In this case, we use a 1 millimeter thickness of water layer, and we irradiate a strong UV light to achieve about 10% solar to hydrogen energy conversion corresponding to the 10% STH bubble formation rate. So this is the actually, you see that the small bubble is going up very quickly and goes outside from the top of this small hole. And then that means that even the rate of gas evolution of 10% STH, no problem for this kind of water splitting panel. Then we constructed a larger water splitting panel. In this case, we constructed 25 centimeter times 25 centimeter. Then the loaded photocatalyst is 0.4 gram. and silica nanoparticle is 0.9 gram. This is a side view of a water splitting panel. Here we have a photocatalyst layer, and this is a gas outlet. And here we have a water inlet. Water is very slowly introduced into this reactor. And the thickness of the water layer in this case is only 100 micrometer, 0.1 millimeter. Then this is an experiment using such a kind of system. And in this case, we use a UV LED at 365 nanometer to irradiate this water splitting panel. I hope that you can see a small bubble is formed and going up, then go outside through the gas outlet. I should say that efficiency of water splitting reaction in this case is exactly the same when we have a millimeter thickness or a centimeter thickness of water layer. That means that 100 micrometer distilled water layer is enough to effectively being split by photocatalyst. In addition to that, we also examine the durability and continuous irradiation of the sunlight. Then our definition of the durability is that the period maintains more than 80% of initial activity. Here I showed one of the typical experiments using this kind of water splitting panel, and this is 1,500 hours. So from this kind of experiment, we evaluated that under continuous irradiation, I mean that the irradiation day and night, that durability was about 1,600 hours. Then we consider that under field test condition, I mean that there is a day and night, and also the clear day and rainy day and cloudy day, and in considering the Japanese weather condition, we evaluated that it is about the durability will be about 1 year. So we decided to construct such a kind of field test systems. Now let me move to the next part, construction of a prototype solar hydrogen production system. Okay, here I show that the whole system structure. These are the water splitting panel, and then evolved hydrogen and oxygen in 2:1 ratio is collected, and these collecting tubes, and then transferred to this gas separation unit. Here we have a gas separation membrane to separate hydrogen and oxygen. Okay, at first we constructed the 3 square meters light receiving area system. And in this case, we use a 48 water splitting panel. And okay, this is a real one. And on the right-hand side, the bubble is coming out. This is evolved hydrogen and oxygen from this 3 square meter system. And in this case, about 200 milliliter per minute of hydrogen and oxygen is evolving. In this case, that the solar to hydrogen energy conversion efficiency was about 0.76%. So we decided then to construct the 100 square meter system at Kakioka Research Facility. That is the University of Tokyo's campus. And this on this small hill, there is a flat places as shown here, like this one. And from this one, we actually used the 1,600 water splitting panel to cover the 100 square meter light receiving area. And here we have a gas separation system. And this is bubbles of hydrogen and oxygen evolving before introducing into our gas separation system. In this particular case, that about 3.6 to 3.7 liter per minute of hydrogen and oxygen is actually evolving. Then, okay, in our project, there is an expert group to develop a hydrogen and oxygen separation system, but I'm not in charge of that task. So here, let me introduce another type of gas separation system. That is a commercially available polyimide hollow fiber membrane. This is actually a purchase from Ube Industries. Then it was actually designed for the cartridge for compressed air dehumidification. So this is not really designed for the hydrogen and oxygen separation, but it does work to some extent. So from here, we introduce the hydrogen and oxygen 2:1 mixture with saturated water vapor at the total pressure is about 1 bar. into this one and then goes outside here. And we actually evacuate to about 0.1 bar. So through this hollow fiber membrane, that extract hydrogen is actually goes outside here. And then the total pressure difference between this membrane is about 1 bar. So we don't need to spend so much energy to separate of hydrogen and oxygen. And this is a real cartridge of such a kind of system. And as you see here, these are actually a polyimide hollow fiber membranes. It's contained about 2,300 hollow fibers, and the length is 32 centimeter, and the inner diameter is 0.3 millimeter. Using this one, we carried out a separation experiment, and in this particular case, almost all day was a clear day, and this is the accumulated amount of hydrogen and oxygen. And in this case, this day we obtained about 1,000 liter of hydrogen and oxygen mixture. And sorry, this is a little bit busy, but this green curve indicates hydrogen-rich gas, filtrated gas composition. And in the evening, in the morning, sorry, we obtained about 96% hydrogen purity. And in the daytime, that purity was about 92 to 93%. And in the evening, it becomes about 95%. The difference of this purity is due to the ability of the hydrogen separation, because this polyimide membrane is separation property becomes worse when the temperature is higher. So in this particular case, from these curves, we obtained that the hydrogen recovery was about 73%. And that then probably, as you know, that the explosion region of hydrogen and oxygen mixture is very wide. So if we avoid the explosion region of hydrogen and oxygen mixture with a hydrogen-rich condition, we need to go beyond the 95%. So as you see here, some part of the separation, we still obtained this kind of still in the explosion region. But this is carried out on the 2020 October 2nd. More recently, we improved this system. Then that after we are now reacting the remaining oxygen by using palladium catalyst. So we can now get about 99.9% purity of hydrogen. And the hydrogen recovery is now about 85%. And our target is about the recovery of about 90%. Okay, so as I showed that we have constructed 100 square meter light receiving area and the solar to hydrogen energy conversion efficiency under the optimum condition was about 0.8%. And that the optimum rate of gas evolution was about 300 liters per hour. This is enough to check our gas separation systems. However, that we need to pay attention or need to do examine more carefully that this one, verification of safety total system operation. As I showed that our system involves hydrogen and oxygen in 2-to-1 ratio. This is obviously explosion gases. So we carry these gases actually to gas separation unit. Then we separate hydrogen and oxygen. So that actually we are working on this type of system for about 3 years. And we have never observed any spontaneous explosion of this system. That means that the probability of the spontaneous explosion is very low. However, from the viewpoint of safety engineering, we need to intentionally cause the explosion at various points. And so far we have done a lot of experiments, but here I show that only 2 experiments of such a kind of safety engineering. And in this case, I show that the gas carrying tubes, this is a polyvinyl tubes, inner diameter is 10 millimeter thickness, 10 millimeter in the inner diameter, and the total length here is 100 meter. And the inside of this tube was filled with hydrogen and oxygen in 2-to-1 ratio and saturated water vapor. Here we have a Tesla coil to cause the explosion. And the outlet is here. It is get into the water layer in 5 centimeter depth. And this is a real-time video, so that reaction takes place instantaneously, like this one. But as you see here, that this tube is not damaged. And this is exactly the same experiment, but observed from the another angle. And then that this is 280 times slow motion videos, like this one. Okay, then you can follow that's how that this explosion proceed, like this one. Okay, and from this video, we can evaluate the rate of this explosion. That is 2,800 meters per second. The velocity of sound is only 360 60 meter per second. So this is much faster than the velocity of sound. So this is a so-called detonation. Although the detonation takes place, as you see here, this gas carrying tube has no damage. So that we are able to do this the same type of experiment many times using the same gas carrying tubes. And probably some of you worry about the gas separation unit. So this is Ube Industries gas separation unit. And actually, it is now separating the hydrogen and oxygen mixture into, and then that this is also a slow motion video. So you can see that detonation proceeds into this reactor, like this one. And this is another angle view. And in this case, we have here we have a window to see the inside of this cartridge. Again, like this one. But as you see here, that there seems to be no change even after explosion. Actually, that we observed no damage or performance of the degradation of the membrane after several explosion or detonation experiments. So at first, we are now carrying this kind of experiment. Now let me summarize my talk. We are developing various kind of one-step water splitting photocatalyst, as shown here. And also simultaneously, we are developing two-step or Z-scheme water splitting system. Here I show some combination of such a kind of materials. And today I discuss these 4 different types of systems. And at present, we are developing a more efficient and stable photocatalyst sheet and water splitting panels. And simultaneously, we are developing more safety total hydrogen system. And then that here I show that our image to install this new technology into the real world. In that case, we now plan to use 1 unit of 10,000 square meter. That means that 1 hectare. It is 100 times larger than our 100 square meter system that I showed in the previous slide. Then in this area, 1 gas separation unit exists. And in the beginning stage, we like to achieve the solar to hydrogen energy conversion efficiency of 3 to 5%. According to our collaborator, industry people say that if 5% will be necessary to commercialize this new technology to install into the real world. So the question is that, is it possible to achieve these numbers? Here I show that our photocatalyst, which can split water into hydrogen and oxygen. And this brown colored dot indicates the 2-step overall water splitting system. And this axis shows apparent quantum rate in a logarithmic scale. And this axis shows absorption rate of the photocatalyst. And today I discuss a little bit in detail about strontium titanate, how to improve the activity like this one. And then that to achieve that about 3 to 5% solar water splitting energy conversion efficiency, then that we need to use this kind of particles. I mean that the absorption edge is located longer than 600 nanometers. So we need to this kind of photocatalyst. Then if we use, for example, this oxysulfide material to achieve solar to hydrogen conversion efficiency of 3%, we need about 20% AQY. If we like to achieve 5%, this is a commercial level, we need to achieve about 30%. And to achieve 10%, we need to go beyond the 50%. If we achieve this number, we can produce a large amount of very cheap hydrogen. But the question is that, is it really possible to achieve these numbers? So here, let me show the one simple equation. The band gap energy of this material is 1.93 eV. And to split water into hydrogen and oxygen, thermodynamically, we need 1.23 eV. So the excess energy is 0.7 eV or 68 kilojoules per mole. And so this is the driving force that we can use to enhance the activity or the rate of water splitting reaction. And we believe that it should be possible to achieve these numbers. So we are now working, focusing our effort to achieve these numbers in the near future, hopefully in a few years. Okay, now, oh, sorry. I think, okay, this is the end of my talk. Thank you very much for your kind attention.
Well, thank you, Kazunari, for your very impressive presentation today. We really appreciate for your presentation. Now, I think I'll open for the session for students first to ask him or comment anything.
I spoke too fast.
There is one question on chatting panel.
Mm-hmm.
Do you think you can read it, or I can convey the question to you?
Please speak by yourself.
Yes, and he appreciates your wonderful speech, and he's very much curious about the gas separation system.
Yes.
Can you briefly introduce the principle of this separation system?
Oh.
Yes.
This one. Okay.
Polyimide separation. Yes.
Yes. This polyimide hollow fiber membrane has a small pores. That small pore is actually in between that hydrogen and oxygen molecules size.
Yes.
So that the hydrogen molecules is easily go through this membrane. But the oxygen membrane, oxygen molecules is a little bit difficult, but it is not perfect. So that our hydrogen-rich gas still contains some amount of oxygen. In addition to that, this very convenient of this kind of organic membrane is that the water molecules is actually possible to go through, even that during the separation of hydrogen and oxygen. That is a very, very good property for us, because that in our another task that there are some inorganic membranes is also being developed. I mean that, for example, a zeolite membrane or silica membrane. But those membranes have to separate hydrogen and oxygen. The gas has to be dried. If it contains water molecules, then those zeolite membrane is actually water is sticked inside of the pore. So that separation ability becomes much worse. So this kind of organic membrane, we consider that although this is not really developed by our group, but this is just purchased from the ube industry. This is very convenient.
Okay. Yes. Any other questions? Yes. And Professor In has to leave earlier, so that he wants to ask you a question
Yes, please.
now. Yes.
Thank you very much for the great talk. Was very impressed, and I have two questions. Did you use pure water?
Okay.
I think, did you use any whole scavenger? Is it really pure water?
Yes, today is my talk. I didn't show any reaction using Hall or electron scavengers or so-called sacrificial reagent. We use just a pure water. And in the case of the oxysulfide photocatalyst, we added a small amount of sodium hydroxide to increase the pH a little bit in alkaline condition.
I see. Second question is, at the end of your talk, you said 0.7 electron volt for the driving force
Yes.
to achieve AQI 55%. What does that mean of 0.7 electron volt driving force? Do you mean to make a photoelectrochemical electrode?
No. Okay. As I show here, that if we use this oxysulfide, yttrium titanium oxysulfide, then the band gap energy is. Can you see my?
Yes,
Yes.
I can see your slide.
Yeah, and 1.93 volt. This is band gap energy,
Yeah.
and to thermodynamically split water into hydrogen and oxygen, we need 1.23 B. So that the remaining energy is 0.7 eV.
Yes.
That is 68 kilojoules per mole. This is excess energy we can utilize.
So how do you apply for that energy?
We can use this energy after photoexcitation. We put the electron holes are produced in conduction band. Yeah,
I misunderstood you. Okay, I understand. Okay, yeah. Thank you so much. It is really great work. If I have any chance, I would like to stop by to see this system someday.
Yeah, please come.
Thank you very much. Thank you so much.
Welcome. Yeah.
So let's continue for students to ask him. And there is another one on chatting panel. Do you think your catalytic system can use seawater directly?
Oh, no, okay. If we use seawater directly, the activity decreases to about 60 to 70%. That is due to the existence of chloride anion, Cl- anion. Cl- anion compete with water oxidation reaction. So if the Cl- anion is oxidized, then Cl radical is produced. It is very easily reduced again by using photoexcited electrons. So to use seawater itself is not really so good idea. But I just like to say that instead of the I might. Oh no, I don't have here. If we use desalinated seawater, do you understand what it is?
Yes.
Yeah, desalinated seawater, and actually Toray company in Japan is one of the biggest desalinated water production company, and then we use the desalinated seawater. Then in that case, we exactly obtain the same activity for water splitting reaction when we use the distilled water. And the cost of the desalinated water is very cheap at present. 1 cubic meter liquid water is less than $1 US. And if we consider that 1 cubic meter of gas phase hydrogen is about 20 Japanese yen, that is our government target in 2050. If we assume that's a cost, then that's the contribution of the liquid water, desalinated liquid water cost is less than 0.4%. That means almost negligible cost. So I believe that it is good to use desalinated water instead of directly use seawater.
That's a good idea. Any other question from students? If not, oh, here is another one.
Yes, please.
Chatting. Does the water inlet supply water continuously in the hydrogen production system? Yes, obviously it is. Yes.
Probably.
So you already have shown that, yes.
Yeah, this
Yes.
water inlet. This water
Yes.
inlet is very slow because that's
Yes.
we don't need to introduce so much, so that only a very little amount of water is necessary per day. So we have some pump to put the water into this water splitting panel, but it works only 30 minutes or something like that every day. That is enough.
Yes.
So
Great.
we don't need to spend so much energy to introduce water. Yes.
So now professors can ask him.
Yes.
Yes. We normally open for student first,
Yes.
then professors. Well, while they are thinking, I have one question. And you have shown photocatalytic sheet produces more hydrogen
Yes.
than powder catalyst. Why is it?
Oh, that's a very good question. And okay. Okay. So as I showed here, for example, okay. In this case, that's the photoexcited electron and holes actually. Okay. Okay. In this case, the Z-scheme water splitting photoexcited electrons are actually used for hydrogen evolution.
Yes.
In this photocatalyst, and in this case, the oxygen molecule capture the photoexcited hole.
Yes.
So that the remaining electrons in this particle and the remaining holes in this particle has to be combined to complete the whole system, right? Then in a suspended system, some kind of
probability would be lower.
Yeah.
For those two catalysts to collide each other.
Yes, and also
something like that. Yes.
They use some redox shuttles, iron 2+, 3+.
Yes.
But if we use our photocatalyst sheet, we can use this kind of electron and hole conducting layer here. So this seems to be works better than the redox shuttle in the suspended system. That's why we can get much better activity.
I see. What happens if you increase the number of catalysts in the slurry system? Then the probability for colliding each other improves, certainly.
Yes, but if we put too much amount of the photocatalyst in an aqueous solution, then that's only a small portion, probably surface portion of the photocatalyst can absorb photons.
Light. Okay.
Yes.
Okay.
So I should say that although that our structure is still very poor, But nevertheless, that actually quantum efficiency is better than the suspended system, as shown here. Yeah.
Okay. Very good. And other questions? So we are getting late, and there is one question. Nice lecture. I think pH is important during operation. Is pH changed? If pH changed,
Oh, during the
I
reaction?
wondered that there any equipment or system for maintaining static pH?
Oh, okay. For example, in this case, that as you see that both hydrogen and oxygen is evolving.
Yes.
So in this case, we use just distilled water, and both hydrogen and oxygen evolves exactly in 2:1 ratio. That
Yes.
pH doesn't change. Okay, so we don't need to control the pH. Always pH is about 6.8. That is because that this our system contains some amount of the probably gas phase carbon dioxide, so that pH is about 6.8, and the pH doesn't change even that the reaction proceeds.
Okay. Are there any comments or questions? Well, if not, I think we have to close the seminar because it's already after 6. So I really appreciate for your participation, and let me introduce our next speaker. Next speaker is week from today, and Dr. Antonino Arico of CNR ITAE in Italy, advanced technologies for green hydrogen production by low temperature electrolysis. So I hope all students enjoyed today's seminar, and I'm very much looking forward to see you all next week. And again, thank you, Kazunori, for your very, very wonderful presentation today.
Thank you very
I
much,
appreciate
Professor.
it very much. Yes,
Yes.
thank you,
Yes.
thank you.
Thank you very
Yes.
much.
Thank you.
Okay, bye-bye.
Bye. Okay. Now seminar is officially closed, and hopefully our TA took photos especially for students. And again, I can say that when you have to miss seminar due to attending a society meeting, then just let our TA knows who you to go to what society meeting. That's all. You don't need any. We believe you all, so there is no any official documents or whatever. Okay, now I will see you all next week. Bye.